Okay, hi everybody. I understand it's Friday afternoon and it's heat wave and whatever. And I just came from Manhattan, so I also sort of a bit slow. So what I'm going to do today, I'm going to do a sort of crash course on hyperbolic groups. And basically, I follow Breiz and Hefliger's book. But in Breiz and Hefliger's book, it's like it's in different places. There are just geodesic metric hyperbolic spaces separately, and then groups, and actually many like theorem for hyperbolic groups, basically theorems for geodesic delta hyperbolic metric spaces, and like you'll see one of them right away. So I'll do one proof in the beginning, and then I will be just telling you what sort of everybody has to know, like if you want to. And also, it will be the analogy with free groups, because so what we considered: word problem, conjugacy problem, like isomorphism problem, membership problem for subgroups, right? So I'm going to comment on this, how things are in hyperbolic groups, and so what can be generalized, what cannot. Okay, so. So we are going to talk about the Schwarz-Milner lemma. Actually, I mean, I think it was in the 50s it was proved by Schwarz, and then like rediscovered by John Milner, like in the 60s on different sides of the globe. So we need some definition. So a metric space X is proper if closed both of finite radius are compact. Okay, for example, a Cayley graph of a finitely generated group is a proper metric space, right? Because of finite radius, so it's just finite. Okay, so now the action of the group on a metric space is co-compact if the quotient is compact in the quotient topology. So open set is like has open pre-image in the quotient topology. And again, like if you have a group, for example, acting on its own Cayley graph, right, then the quotient space is just 1 point, so it is compact. Now, the Hausdorff distance is defined the following way. So we have two sets, like A and B. Okay, so for each point, we take infimum of distances to points. For each point of A, we take infimum of distances to points of B. And then we take supremum of this for all points of A. So it's basically like the maximal supremum of possible distances from points of A to B and from points of B to points in B to A. Okay, so the Schwarz-Milner lemma actually, okay, so like I mean this is a classical result, like in spirit of like Felix Klein program. So if you have something, if you know something about the action of the group, like what do we know about the group? So suppose we have a proper geodesic metric space, and the group acts co-compactly and properly discontinuously on this metric space. So properly discontinuous means that for any compact K, the number of points so that like gamma shifts of K intersect with K non-trivially is finite. If you have a compact, like all elements except for finite number shifted to something non-intersecting with it, right? Only finite number of elements in the group shifted to something which intersects with the original compact K. Okay, so then the group is finitely generated. Again, like we know something about the action, the group is finitely generated, and for any point x naught in X, the map from the group into a space defined as like gamma is mapped to gamma acting on x0, to the result of action of gamma on x0, is a quasi-isometry. And so quasi-isometry, you remember, like the distance between the images less or equal than c times distance between pre-images plus a constant, not c, lambda plus a constant, and greater or equal than 1 over lambda, distance between pre-images plus a constant. And the group is equipped with a word matrix, as we defined. Okay, so, and this we are going to prove just to see whatever, how things work, or like how proofs work. Okay, so first of all, if the group is finite, then it is obvious. And if X is compact, it is also easy. So we will assume that, I mean, if the group is finite, first of all, it is finitely generated, certainly, right? And it's not hard to show that this mapping is quasi-isometry. So suppose that group is infinite and X is non-compact. But we know that the whole X is like the union of transforms of some compact set, right? So we take a ball, take a radius r large enough so that gamma transfers of the ball of radius r just covers the whole space, the whole X. Okay, now for the closure of this ball, so the closure of this ball is a compact subspace, right? Because this is a condition of the theorem. So the number of elements which such that the S like shift of B intersects non-trivially with B, the number of such elements is finite. And actually we are going to show that this set of elements is actually a set of generators. So, okay. Now, let's just introduce some constants. Unfortunately, in hyperbolic groups, I mean, you have to compute. Like, maybe everywhere you have to compute. Like, but here you have to compute things. So take the infimum of the distance between closure of B and gamma B for elements which are not in the set S. So when the intersection is actually empty. Now, since B bar is compact, so from finite cover, from a cover we can select a finite subcover. So there is this infimum. Actually, infimum is exists, and it's not zero. Like so, let R be this number, and then okay, let lambda be the maximum of distances between x naught and s x naught for s in S. So we have this important set S, the set of all elements which transfer B bar into something intersecting with B bar, right? Okay, so we want to prove that this set S, which is finite, generates the whole group. We want to prove this inequality, which will imply that it is a quasi-isometry, because L of gamma in generators of S, it is a length of gamma, and what we show, so this shows that the mapping from so the length of gamma less or equal than some constant times this distance in the space plus 1 and greater or equal than this, and it shows that they are quasi-isometric, that this is a quasi-isometry mapping between the group and the space. And then C, okay, the C is actually obvious, because for any point, I mean, the whole space is covered by translates of this B bar, right? And so therefore for any point X, there exists some element gamma, so that X is the distance of the translate of X naught by gamma, distance is less or equal than R. Okay, so C is obvious. And actually, this is obvious because the length, the distance between x naught and gamma x naught is less or equal than, like lambda is the maximum distance between x naught and x naught. So this distance less or equal than lambda times length of gamma. So we have to show that S generates a group, and we have to show like B, the second part of B. Okay, so what we do, let me just draw the picture. So first of all, okay, take some gamma which is not in S, okay, because those which are in S, they are generated by S. So take some gamma which is not in S, and now since it is not in S and not identity, there exists some number k such that the distance between x naught and gamma x naught, so less than r plus kr, but greater or equal than r plus k minus 1, lowercase r. I mean, k is greater than 1 because gamma is not in S. And then we'll just start accumulating whatever k's, and then eventually, so the distance is finite, so eventually there is such a number k. Okay, and then we choose x1 xk plus 1 like this. Eraser. I'll just write here. It's a lot of whiteboard. Okay, so let's do it like this. So x1 okay, xk plus 1. So we'll okay, the distance of x0 between x0 and x1 is less than r, and the distance between xi and xi plus 1, so this is going to be xi, going to be xi plus 1, is going to be less than lowercase r, and okay, now each of them belongs to some translate of this ball B. So for example, okay, there is this ball B, and there is point x naught. So this is gamma I minus 1 x naught. This is, they do intersect, right, because the distance is so this is gamma I x naught, and so on. Like so, just this is xi plus 2. Okay, so okay, so we choose these gammas. So we set Si to be gamma I minus 1 inverse times gamma I. Okay, and so what we're going to do, we're going to show that this Si belongs to the set S. So our, like, if you choose Si like this, then gamma is the product of S1 Sk. Right? Now, okay, so this distance between B bar and Si less or equal than the distance between where I wrote gamma I minus 1. Okay, yes, between element here, between x0 and Si x0, right? Which I can rewrite like, because this is actually, this belongs to B0, and this belongs to B, to like, no, I'm confused. So Si is like this, Okay, yes, right. If you do gamma, I think it's just the distance between x0 and
xi plus 1.
yeah, and xi plus 1. So this is so basically we have this, right?
And they're the same distance.
Yes, this is the same. No, this is less or equal because these are points in this sets, and this is equal, and this is less than r by selection of our points, right? So what we have, I mean, R was infimum for elements such that this intersection is empty, right? So therefore Si belongs to S, and therefore the set S generates gamma. And also, okay, so this is less or equal than K. This is by selection of our points is less or equal than 1 over r times the distance, times this distance, plus this. And okay, we just replace r minus r by 1, and so we have this quasi-isometry, we have this inequality. Okay, so that's it. So let me return to the statement. So basically what we have, so if we have a proper geodesic metric space and the group acts co-compactly and properly discontinuously on this space, then the group is finitely generated, and for any point in this space, so this map is a quasi-isometry. Like later on I will formulate. This actually gives another definition of a hyperbolic group, but we will need something else because there are definitions of hyperbolic group which just say that it acts on a like proper delta hyperbolic metric space, geodesic metric space, right? But we need something else for that. Like it's to show that this is equivalent to our definition as group is hyperbolic if all triangles in the Cayley graph are delta thin. We need something else, like to prove this. So, okay. But as immediate corollary, we can have this result, which we had as an exercise, right, before. So if you have a finite index subgroup of a finitely generated group, then this finite index subgroup is quasi-isometric to the group. I mean, because K acts on the Cayley graph of gamma, like properly, discontinuously, and co-compactly. And because it has finite index, so it acts co-compactly. The quotient is finite set, quotient over the like the graph of orbits is a finite set. Okay, and then it is quasi-isometric to the Cayley graph, and the Cayley graph is quasi-isometric to the group itself. So that's another proof of this exercise. Mm-hmm.
So where the distance of gamma I minus 1 inverse xi y I minus 1 inverse xi minus 1, it equals distance of xi and xi plus 1 because you're pulling.
Yeah, because I'm pulling by, because what is this, right? It's gamma I minus 1 inverse gamma I, so gamma I cancels, so I'm just it's, since it is an isometry, like the action is isometric action, so it's quality. Mm-hmm. Okay, so that's the only proof I wanted to do. Okay, so in the following, we have that X is always a geodesic metric space. So there is a very important notion. We know what is a geodesic. It's a shortest path, right? What is a quasi-geodesic? It's quasi-isometrically embedded interval, right? And the very important theorem about delta hyperbolic metric spaces. Again, so this is not about groups. It's about delta hyperbolic metric spaces. But I mean, since it's about delta hyperbolic metric spaces, it's about Cayley graphs of hyperbolic groups. So what it's basically what it says that let me just draw the picture. If we suppose we have a quasi-geodesic between 2 points pinpoints okay, quasi-geodesic. So it's a map of the intervals C of A. This is C of B. And this is a geodesic, which I denote A, B. I will be denoting geodesics like this with square brackets. Okay? So the theorem says, like I will read it later, it says that the distance between points on the quasi-geodesic and geodesic is bounded in terms of constants, in terms of the following thing. So delta is a hyperbolicity constant of the space, and if we have lambda epsilon quasi-geodesic, then this lambda epsilon quasi-geodesic is at Hausdorff distance less or equal than some constant depending on delta, lambda, and epsilon. So this is what's called like stability of quasi-geodesics in hyperbolic geodesic metric spaces. So quasi-geodesic is not far from the geodesic. But certainly how not far? This depends on the hyperbolicity constant and on like constants for this quasi-geodesic. It's always lambda, epsilon, quasi-geodesic. I mean, this is okay. This requires the proof. If you look at Bryce and Hefliger, whatever, a couple of pages of lemmas, and but you can like, read it there, for example, and in many other places too. Okay, so now this is very good because how we define? We said that the geodesic metric space is hyperbolic if geodesic triangles are delta thin, right? But now we know that, okay, so if we have a geodesic triangle, which is delta thin, so if all geodesic triangles are delta thin, then actually, like if we fix quasi-isometry, if we fix constants of for quasi-geodesics, for example, we have some quasi-isometric metric space, then quasi-geodesics are not going to like go too far from geodesics, right? So quasi-geodesic triangles so these are geodesics which are delta thin. Quasi-geodesic triangles are also going to be thin, but just with other constants. So so for, and this is a corollary, so geodesic metric space is hyperbolic if and only if for every lambda and epsilon there exists a constant term such that every lambda epsilon quasi-geodesic triangle is M slim, or like M thin. Now, but then, so suppose we have a quasi-geodesic metric space which is at the mapping from there into delta hyperbolic space, which is quasi-isometry. Then the first space is also hyperbolic because like it's quasi-isometric to so triangles are thin, geodesic triangles are thin here, but geodesic triangles in Y go to quasi-geodesic triangles in X with the same constants, right? Because it is we have a KC quasi-isometry between Y and X. So constants are the same, therefore there is a constant such that geodesic triangles in Y, which go to quasi-geodesic triangles in X, are also thin, like with this constant, and therefore Y is also hyperbolic. And so this actually implies that hyperbolicity is a quasi-isometry invariant, right? Only now we can, like only after we know about stability of quasi-geodesics, we can actually prove that hyperbolicity is quasi-isometry invariant. And that, for example, the property of a group to be hyperbolic does not depend on the generating set, because if we change the generating set, we have Cayley graphs are quasi-isometric, so like one is hyperbolic, then the other is hyperbolic. Okay. Now after we know that hyperbolicity is quasi-isometry invariant, we can, using this Schwarz-Milner's theorem, we can give equivalent definition of a hyperbolic group. So a group is gamma is hyperbolic if it acts properly, discontinuously, and co-compactly by isometries on a proper hyperbolic metric space. Like Schwarz-Milner lemma says that if a group acts properly, discontinuously, and co-compactly by isometries on a proper geodesic metric space, then it is quasi-isometric to this space, right? So if this space it acts on is hyperbolic, then since group is quasi-isometric to this space, then the group is hyperbolic itself. So I mean, this does not use thin triangles, so this is just if you manage to find such a hyperbolic metric space where the group acts nicely, then it is a hyperbolic group. Now examples of hyperbolic groups. So free groups, for example. Free groups are, what is the hyperbolicity constant? Zero, right? Because geodesic triangles in a free group are just tripods. I mean, there are actually no relations, right? So if you have a Cayley graph, it is a tree. So geodesic triangles look like this, like G1, G2, G3. So you go like this, and this. So they're very, very thin. Just on the strict diet. That's eating too much here. That's kind of will become non-hyperbolic by the end of the, like, at least I will become. Okay, so another example. If you have a closed hyperbolic manifold, then fundamental group is word hyperbolic. Also Schwarz-Milner's lemma. And there are many other examples, like closed surface groups we already discussed, right? So, closed hyperbolic manifolds. So surface groups are hyperbolic. Okay. Now also, yeah, non-examples. Z to the n is not hyperbolic. So free abelian group is not hyperbolic, right? Because triangles are fat. Like it's geodesic triangles. So if you have, let's take Z square. This is a Cayley graph, right, of Z square. Okay, so take 3 points, this, and this. I mean, this is a geodesic, right? It's the shortest path. So geodesic, but this is also geodesic between these 2 points, right? And any of those is geodesic. Now, if these points are at distance 4, as soon as I mean, you can see that this is a geodesic triangle, right? And we cannot bound like the distance from one side to the union of the other two by any constant, because if I make it of this side of length 5 and like n, when n goes to infinity, it becomes fatter and fatter and fatter. So, and actually a hyperbolic group cannot contain Z2. Like no hyperbolic group contains Z2. And actually it also cannot contain any Baum's-like solitaire group, except like if it is, no, it can't contain any of them. By the same reason, we can make fat geodesic triangles, fat diagrams, if you wish. Okay, so and then, so if you want to prove some nice properties, which we proved for subgroups of a free group, like what are nice properties? For example, the intersection of 2 finitely generated subgroups of a free group is finitely generated, right? Yesterday we constructed, we even can find a basis if you remember we took Stolling's graphs for H and K, took the product graph and proved that this product graph is actually like Stolling's graph for the intersection of H and K. I mean, connected component of this product graph. like a connected component containing the initial vertex. So if H and K were finitely generated, then the product graph also has finite number of simple loops, so the intersection is finitely generated. This is called Hausen property. And it's not always true. I mean, I'll talk about examples. Not always true in the group that intersection of two finitely generated subgroups is finitely generated. So Hausen property. Also, membership problem was decidable into a subgroup, right? Like given an element, we could decide whether it belonged to a subgroup of a free group, finitely generated subgroup of a free group. Like if we can read this word in the Stolling's graph, then it belongs to a subgroup. If you cannot, it does not. Also, word problem was decidable. Conjugacy problem was decidable. Isomorphism problem was decidable for two free groups. So we would like to, but if we want to get nice properties for subgroups, we have to consider quasi-convex subgroups in a hyperbolic group. So what is a quasi-convex subgroup? A subspace of a geodesic metric space is quasi-convex if there is a constant such that geodesic, basically the same picture would work. So take 2 points of the subspace. Take a geodesic between them, right? No, the same picture is not going to work. Let's do another picture. This is K, right? And then take 2 points in K, x1, x2, right? Y1, 2. This is a geodesic, but this is a geodesic in the big space. But quasi-convexity means that this geodesic is not far from, like the distance from this geodesic in the larger space. It is a bounded distance from K. Okay, so this means that K is quasi-convex. So for any point x on the geodesic in the larger subspace, I maybe had to curve this K, but it's okay. So a subgroup H of a hyperbolic group is quasi-convex if it is a quasi-convex subspace. So this means that if we have a path from, like, take identity element in the group, take a path to element G. This is our element H in H. Okay, and this is H in H. This is H. Then each point is the bounded distance from H. So this is what is a quasi-convex subgroup. So for the geodesic in G to element from H is at the bounded distance from H. And again, like there is some constant of quasi-convexity, certainly. I mean, groups can be like lambda, subgroup can be lambda quasi-convex. So, okay, so if we consider again Z2, example of not quasi-convex subgroup in Z2. So if this is A, this is B, so suppose Z2 is generated by like A, B, commutator A is equal to 1, and take a group, let's say C, generated by AB, by the product. Okay, these points. It is not quasi-convex because, I mean, for example, it should be for any, the property should be true. So for all x on a geodesic, right? And for any geodesic, I maybe had to put one more quantifier. For any geodesic, like this is geodesic between this point and this point, right? This is a geodesic, but it is far from the group. And if I take like AB to the power 100, there is again like this geodesic, which is going to be further and further like from the group. There is a geodesic which is in the group itself. It is quasi-isometric, it's even isometrically embedded, right? But it is not quasi-convex. So for example, like Z2 may contain quasi-isometrically embedded subgroups which are not quasi-convex. Okay, but so this is like this example, and L1 metric. This means that we're going like it's Manhattan metric. We're going like this, not Euclidean metric. Okay, but since in a hyperbolic group we have this stability, which I erased, stability of quasi-geodesics, actually for hyperbolic group and subgroups of word hyperbolic group, quasi-convexity in some or like any Cayley graph is equivalent to a subgroup be finitely generated and be quasi-isometrically embedded. Like I just showed you an example of a subgroup which is quasi-isometrically embedded in Z2 but not quasi-convex, right? In hyperbolic group, quasi-isometrically embedded and finitely generated is equivalent to being quasi-convex. Okay, the proof. Let's see. So if it is finitely generated and from the theorem, let me show the theorem. This was the theorem, so the theorem about stability of quasi-geodesics, right? So if it is okay, so if it is right, if it is quasi-isometrically embedded, then since quasi-geodesics are not far from the geodesics, so it is quasi-convex, and it is finitely generated also. Now suppose H is quasi-convex, fix a generating set for gamma, and so we want to show that H is finitely generated and quasi-isometrically embedded, right? Okay, so take some element H in H. Now H is quasi-convex with constant K. So like this is a, suppose this is a geodesic in the group G, in the group gamma, to this element H. So since S is a generating set, so this are like, it's a product S1, S2, S so on, Si, and so on, right? Okay, but geodesic is not far from H because the subgroup is quasi-convex. So I just draw this like this path, which all shorter than capital K. Okay. Now let me. All shorter than capital K. So I just again, like I'm just going to go to the other slide. So this is my geodesic two element from H, and then I made this picture. Now I just repeat it. It's completely the same picture. Okay, so I mean these distances are less or equal than K, and these elements are less or equal than K. Now let Hi be like Gi minus 1, like for example H2. It is G1 inverse G2, right? G1 inverse G2. But each Hi is actually, what is the length of Hi? K plus 1 plus maybe another K, right? So each element hi has in the large group length not larger than 2k plus 1, because I mean it is shorter or equal to k plus 1 plus k. Okay, so what we got? We got that each element in the subgroup H is a product of these elements H1, H2, Hi, and each of these H1, H2, Hi is shorter than 2k plus 1 in the larger group. Okay, but it's a finite number of such elements, right? First of all, it's a finite number of such elements, so it is finitely generated. And then it is quasi-isometrically embedded, because, I mean, take a maximum length of this Hi. So quasi-convexity is the same as be quasi-isometrically embedded and finitely generated in hyperbolic groups. Okay. Now example. In a free group, every finitely generated subgroup is quasi-convex. Let us just prove this. So that in a free group, every finitely generated subgroup is quasi-convex. Did not write it down here, but I'm actually going to prove a little bit more general fact. Okay, so it should be an arrow here. It's not good to write slides in the car. So don't write slides while driving. Even GPS does not allow this, because then you make misprints. So no, I was staying in traffic yesterday, going to Manhattan, and just doing something with the computer. Okay, so homomorphism from H is a subgroup of G. Homomorphism from G to H is a retraction if it is identical on elements from H, right? And H is called a retract of G. Now, if we have a retraction from G to H, and G is finitely generated, then this inclusion, so H is a subgroup of G, but then this inclusion of H and G is quasi-isometric embedding. We just have to prove it for some generating sets, right? So take generating set of, first we take generating set of H, and then extend it to generating set of G, right? Now, the shortest way to write elements of H in G is just as a product of generators of generators of H. Again, take generators of H, and then extend them to generators of G. So to write element of H in H, the easiest way, the shortest way, is to use this generators of H, and then it is an isometry. Now, yesterday we proved Marshall-Hall theorem. What it says, that if you have a finitely generated subgroup of a free group, then there is a subgroup of finite index, L, right? Let me write it down before. So, if you have H, subgroup of F, finitely generated, and then there exists L, which is actually H free product with K, right? And L is finite index of in F. Okay? Now, so then there is a retraction from L to H, right? We just sent whatever, basis of L consists of basis of H union basis of K, right? Send all elements from the basis of K into identity, and we have a retraction to H. So H is so H is quasi-isometrically embedded into L, right? But L has finite index, so it's quasi-isometrically equivalent to the whole group, right? So then H is quasi-isometrically embedded into the whole group. So for a free group, so this F is free. So for a free group, if you take a finitely generated subgroup, it is quasi-isometrically embedded, and this is equivalent to be quasi-convex, right, for hyperbolic groups. And
So in the exercise, I don't see why
G is finitely generated, then the inclusion is maybe I should say that H is finitely generated here in the exercise, or maybe it's true for not finitely generated. Let me see. So right finitely generated, just I mean, but you're getting my notes. So corrected for finitely generated. Or think, do it as an exercise. Is it true for infinitely generated? So if I wrote it again, it's for finitely generated, it's for sure true. It's maybe it's true for infinitely generated. So
homomorphism is not necessarily epimorphism, right?
No, it is an epimorphism. It's a retraction. So retraction means whatever. So it is an epimorphism. It is an epimorphism. So maybe I just didn't write the definition of retraction correct.
No, it's okay.
So it's onto. I mean, it's epimorphism here in the definition of retraction is an epimorphism.
Yeah, I mean, it's
Yes, right. It is identity on H, so it's right. H?
Like H has to be finitely generated because you just look at images of the generators of G.
Right. Yes, right. Okay. Yeah, it is finitely generated. Yes, automatically. Okay, so now the theorem. I have some time. Now this is all non-trivial. These are all non-trivial results by different people. Like quasi-convex subgroups of hyperbolic groups are hyperbolic. If a subgroup is non-quasi-convex, we'll talk a bit later. It doesn't have to be hyperbolic. So in a free group, all subgroups of a free group are free. In a hyperbolic group, maybe subgroups which are not hyperbolic. But if it is a quasi-convex subgroup, then it is hyperbolic itself. So basically, to prove something nice about subgroups, you have to take hyperbolic subgroups, because otherwise, like, there are dragons and things can go very wild. Now I'll show how wild things can be if I come to discussion of Reeves construction. Okay, now intersection of two quasi-convex subgroups is quasi-convex. By the way, quasi-convex subgroups are finitely generated, right? From that theorem, if quasi-convex, then quasi-isometrically embedded and finitely generated. So when we say quasi-convex, they are finitely generated. So intersection of two quasi-convex subgroups is quasi-convex. So in particular, Hausen property holds for quasi-convex subgroups, right? And then membership problem in the quasi-convex subgroup is decidable. You certainly have to know the quasi-convexity constant for that, right? But quasi-convex subgroup is quasi-isometrically embedded, right? And therefore, again, like if you know constants, then this means that you cannot write an element in a subgroup. You can bound the length of representation of your element in a subgroup. So you have your element. It is geodesic, written as geodesic in a larger group. But since it's quasi-isometrically, the subgroup is quasi-isometrically embedded, you can bound the length of this element in generators of H. And then you just try all this, like all words in H and solve the word problem, which is like also has to be discussed. So, for example, this one can play with, if we have an element of infinite order, then the centralizer is quasi-convex. Actually, in a hyperbolic group, if an element has an infinite order, then the centralizer is like, it's a virtually infinite cyclic subgroup, so finite extension of infinite cyclic subgroup. And it is quasi-convex. This is like this bad Baum-Slack solitaire group, which cannot be a subgroup of any hyperbolic group. And again, one can construct diagrams with triangles which are not seen, like in Z2, basically. Okay. Now let me return to Dehn's presentation. I mean, I still, I already defined last time Dehn's presentation. Let me define it again and talk a little bit about it. Like how to prove that every hyperbolic group has Dehn's presentation. Okay, so symmetric presentation is Dehn presentation if for any reduced word which is equal to 1, there exists a relator so that R is R1, R2, the length of R1 is greater than the length of R2, and this word contains R1 as a subword. So in Dehn's presentation, every element which is equal to 1 contains more than half of some relator. Since we have symmetrized set, so we can say that it contains more than half of the beginning of some relator. Okay, so why hyperbolic group? I mean, this is about complexity. Actually, now there are very many interesting questions about complexity of different algorithms in hyperbolic groups. I mean, it was like a first wave of research when people proved like decidability of these problems, but it's interesting like what is time complexity of algorithms, what is space complexity of algorithms, what is actually like doable, what is not, because like we have Dehn presentation. Hyperbolic group has Dehn presentation, but okay, go find this Dehn presentation if you are given generators and relators of a hyperbolic group. Also, if you are given just generators and relators, you cannot decide if the group is hyperbolic. I mean, in general, this is so-called Markov's property. So this is Markov's property to be a hyperbolic group. And long time ago, in 50s, Markov proved the following thing, that there is no any algorithm to decide the Markov property if a group satisfies Markov property, if a finitely presented group satisfies a Markov property. All what you need for Markov property is that this is a property such that there is a group with this property, hyperbolicity, for example, and there is a group which is not embeddable into any group with this property. Like, for example, Z2 is not embeddable into any group with this property. And then the property is like, there is no algorithm given a finitely presented group to decide whether it has this property or not. It's not only hyperbolicity is undecidable, whether the group is trivial is undecidable, whether it's abelian is undecidable, whatever, it's again dragons. So I'll skip this because it's complexity. Okay, so I'll skip surface group. We did these examples. Another definition, just to talk a little bit about Dehn's algorithm. A path is called k-local geodesic if every subpath of length k is a geodesic. I mean, the path is not necessarily geodesic itself, but every subpath of length k is a geodesic. For example, if you take a sphere of radius 1, a great circle is like pi local geodesic, right? So subpath of length less than pi is geodesic, but I mean, if you have a longer path, it's not. Now, and this is again, this is non-trivial, but in a delta hyperbolic group, if you have 4 delta local geodesic, this I skip. If you have a 4 delta local geodesic and a delta hyperbolic group G, then this geodesic is contained in 3 delta neighborhood of the geodesic between endpoints. Okay, now why hyperbolic group has Dehn's presentation? Basically, to get Dehn's presentation, you can like think about this as about exercise. If you take all words which represent identity and shorter than 8 delta, so take a hyperbolic group, take all words of length shorter than 8 delta that represent identity, and use them as relations. So this is going to be Dehn presentation. So basically, just take all words which are short enough, because like the simple way to show it, I have time to talk about ribs a little bit. But like best way to show it, okay, so have, suppose the word is equal to identity. Like I skip trivial cases, but okay, if it is like, if it has length less than 4 delta, this is a relation, right? If it has length longer, then okay, it represents identity. It is contained in the now it represents identity. It contains in 3 delta neighborhood of the origin, right? Because geodesics joining these 2 points is just empty path, right? And then, so basically what we do, like, if it is, so we take a path of length 4 delta. If this is not 4 delta local geodesic, then there is a shorter path. And this relation has length like 4 delta plus something shorter than 4 delta, so less than 8 delta. And you just go on, or something like this. Sorry, it's like no time already. Again, you can read it in like Hefliger. Conjugacy problem is decidable. Word problem is decidable. It's a very interesting question whether like there is a polynomial time algorithm to find, like suppose you know that the group is hyperbolic. How to find Dehn's presentation? I mean, it's if you can find it. There is an algorithm to find it, but can you find it like fast, relatively fast? Because enumerate all elements of length less than 8 delta, but also one has to find delta. Suppose you're given a finitely presented group. You're told that it's hyperbolic. How do you find delta? It's possible. I mean, one can construct an automaton, and like this is something I wanted to talk, but I don't have time. Like Gulnara and Alshansky did something like this for random groups, and Karpovich did something like this for Karpovich. Computed the constant, and we constructed, like it's myself, Mesnikov, and Weil, algorithm to construct a Stallings graph for a quasi-convex subgroup, like Stallings-like graph, because the graph is different in a hyperbolic group. So there are loops corresponding to relations, but one can construct something like a Stallings graph. Now, I don't have time at all because I wanted to talk about Rips construction, but just explain where the dragons are coming from, so that you know the words Rips construction. So what is interesting, like the construction is as follows. It turns out that like you can take any finitely presented group Q and construct it as a quotient of a small cancellation group. Like you take any finitely presented group Q with an undecidable word problem, very, very like bad group. You can get it as a quotient of a small cancellation group, so in particular hyperbolic group, with finitely generated kernel. And this gives like all these examples of finitely generated subgroups with undecidable membership problem, finitely generated but not finitely presented subgroups of hyperbolic groups, like all the dragons, many dragons, and I think it's one of the few constructions which whatever gives dragons, which for non-quasi-convex subgroups. And the idea actually like very simple. So you take relations of these group generators and relations, add 2 more generators x and y, and produce noise, like change these relations, like putting like big powers x and y between them and so on. And you can easily do small cancellation, right? I mean, depends how you add this x and y. So add them the way that there are no common pieces. So you got the small cancellation group, like 1 C prime or 1 6 or whatever you want. Now, but if you now kill an x and y, so now consider homomorphism from G to Q, just kill x and y, map them into the identities, then you have this group Q. And the kernel is just generated by 2 elements. So just x and y generate the kernel. So such a beautiful construction, sort of like you begin with arbitrary group, and then like adding noise to relations, so you make it small cancellation, and then this way in small cancellation groups you get like all unpleasant things which you could get in this like finitely presented, arbitrary finitely presented group. Okay, and so I'm finishing. There are many open questions. I have emailed the slides so you can look at this. Like this is an old question of Gromov. This question like free groups are residually finite. About hyperbolic groups we don't know. This is equivalent. This is equivalent to 2. There is a paper by Karpovich which shows that this is equivalent. And this is about Dehn presentation, like about. But also, like for all the algorithms, it's interesting to find time complexity and space complexity, and like for example, what is in log space. My student, Nicholas Tuikan, my former student, long time ago, he constructed almost linear algorithm for Stolling's graph, for construction of the Stolling's graph. Almost linear means linear times this whatever very, very slowly growing function, logarithm star function. And actually the same complexity, he just recently constructed an algorithm to like for SL2Z, it is virtually free, so has a free subgroup of finite indexes we discussed. So, but you also can construct like Stolling's graph. So, and the same also algorithm is very fast and very clever.
He did it by hand.
He did it by hand, yes. Okay, so I mean, short algorithms, fast algorithms are sort of important. Thank you very much.